Hello everyone. Today's topic is Laplace transforms. Okay, let us learn about this topic. Now here, if you observe in this unit, we have two parts. That is first Laplace transform. Another one is inverse Laplace transform. Okay, almost the same topics will be there in both Laplace and inverse Laplace transforms. And here, if you observe in Laplace transforms, we see the basic problems. Under the basic problems, we see how to use the formulae, Laplace transform formula, all these things. And second, we shall see the first shifting theorem. And the third topic is second shifting theorem. Okay. Here, the first shifting theorem, some subtopics are there. And we shall see unit step function and everything. Here, change of scale property, a small topic is there. It's not actually a subtopic. And these are the main topics. Okay. And next here in this case, now the fourth topic is, if you observe the fourth topic, the fourth topic is Laplace transform multiplied by t power n. And fifth topic is Laplace transform divide by t power n, t power n. And sixth topic is Laplace transform of derivatives. And next is seventh topic is Laplace transform of integrations. And the last topic, eighth topic in the first part is the application part. Under the application part, we shall see the use of the Laplace transform. That is, there are some integrations will be there. Integrations. Those integrations we can find suppose integral 0 to infinity. Some integrations will be there. The complicated, sometimes impossible integrations can be found using Laplace transform. So in this here we find evaluation of integrals, the application part. Okay. And next in the second part, that is inverse Laplace transform, we shall see the topics like basics. Under the basics, we shall see the inverse Laplace transform, what you call formulae and how to use them, and as well as using partial fractions, using the partial fractions. Okay. And second topic is first shifting theorem. And the third topic is almost similar topics will be there. Here, the first shifting theorem in Laplace transform. Here, first shifting theorem in inverse Laplace transform. Here, the second shifting theorem in Laplace transform. Here, the second shifting theorem in inverse Laplace transform. Like this will be there. Okay. And here, the Laplace transform multiplied by t power n. Here, inverse Laplace transform multiplied by s power n. Okay. And fifth topic here, Laplace transform division by t power n. Here, inverse Laplace transform divide by s power n. And next, the sixth topic is here, Laplace transform of derivatives. Here, inverse Laplace transform of derivatives. And here, Laplace transform of integrations. Here, seventh topic, same, almost similar, inverse Laplace transform of integrations. Okay. Eighth topic is a different thing, convolution theorem. Okay. In the convolution theorem, we shall see some problems involving the inverse Laplace transform. And the ninth topic is the application part. Here also application part. The use of Laplace and inverse Laplace transform is to solve ODE, ordinary differential equations. Here we shall see about the solving of ordinary differential equations. Here we need both Laplace as well as inverse Laplace transform in the applications. The use of the Laplace and inverse Laplace transform is to solve the ODE, and only using Laplace transform we can evaluate integrals. We can evaluate integrals using that. Okay, these are the topics, out of which the convolution theorem and solving ODE are very, very important, and never seen any question paper without these two topics. Okay. So without any no time, so we shall move to next topic. Okay. Here we shall see actual definition of Laplace transform. Okay. Here in this case, before learning what is Laplace transform, we must know what is integral transform. What is the integral transform? we shall see the definition of integral transform. From the integral transforms, there are many transforms, not only Laplace transform, there are many transforms like Laplace transform, Fourier transform, and Z transforms like this. There are many transforms. So out of which, for all these things, the basic thing is the inverse, that is integral transform. Here we shall see the definition of integral transform. Any integral transform, that is any transform means Laplace, Fourier transform, Z transform, all these things based on this definition only. The integral transforms are defined by I of f of t is equals to integral minus infinity to infinity. So here k of st, shall say k of st. So this is a function of s and t, and here f of t dt. Okay, here any integral transform transforms a function of s to function of t. Sorry, any integral transform transforms a function of t to function of s. All inverse transforms transforms the function of s to t. Okay, so these are the cases in any transform. The transforms a function of t to function of s. Here we integrate with respect to t and substitute the limits, so t will be eliminated and we get only a function of s. Okay, so that's the thing. And here this is the integral transform definition. Integral minus infinity to infinity k of st f of t dt is called integral transform. Okay, and here it is denoted by f bar of s, and I of f of t can also be written as f bar of s. Okay, or any integral transform. Now here the function k of st is called kernel of f of t. Kernel of f of t. Okay. So here in this case, the kernel k of st is called kernel of the function. Kernel of the function. Okay. So now, if we change the kernel, it will transform into some other transforms, some Laplace to Fourier, Fourier to Z transforms like this. We have to substitute k of st. Now here I'll substitute k of st, the kernel, as the function e power minus st if t is greater than 0 and 0 if t is less than 0. Okay, this is the kernel, and if we substitute the kernel, it transforms to the Laplace transform. Here, the Laplace transform of f of t, a function, is denoted by L of f of t. Here, always any transform, we write here flower braces. We cannot write square brackets or parentheses. So we have to use only flower brackets. Okay. And as well as it can also be denoted by f bar of s, as every transform is denoted by f bar of s. Here, Laplace transform also denoted by f bar of s, because the function of t is changed to function of s. Okay. And next here, now here, since the kernel is defined from t is greater than 0, that is 0 to infinity. So the limits will be 0 to infinity instead of minus infinity to infinity. Okay. If you see the Fourier transform, the limits are minus infinity to infinity only. Here, the Laplace transform 0 to infinity. The present topic is Laplace transform. So in the place of kernel, and substitute here e power minus st, f of t dt. We integrate with respect to t and substitute to t limits, we get a function of s alone. So the function of t is transformed to function of s. Okay. And here in this case, last topic, evaluation of integrals. Suppose the evaluation of integrals, any integral 0 to infinity form, 0 to infinity form only we can find. And here in the function, suppose it's a function of t. So in this function, in this order, in this form, the integral may be complicated or impossible to find. So we transform this into s and solve the integral. And here also ODE, sometimes it is very difficult and impossible to solve. In that forms also, if the ODE is in function of t and y. So y is a dependent variable, t is independent variable, and we change the function of t to s and solve this differential equation. And again, we apply inverse Laplace transform. The function, the solution will be in s. So we transform to s to t using the inverse Laplace transform. So first we apply Laplace transform, change t to s and solve the ODE. And then again, we apply inverse Laplace transform, function of s to t. So like this, we solve it. So the The main use of the Laplace transform is to evaluate integrals as well as to solve the ODE, that's ordinary differential equations. So, okay, if you see the definition, so here the way, so this is the definition of integral transforms. Any integral transform is denoted by var of s, integral 0 minus infinity to infinity, k of st, which is the kernel f of t dt, where k of st is known, is a known function of s and t called the kernel of the transform. Based on the kernel, the transform is defined, Laplace or Fourier or something else. Okay. Here in this case, the kernel is e power minus st for 0 to infinity. So the Laplace transform is defined by integral 0 to infinity e power minus st f of t dt. Okay. So this function is known as the Laplace transform. So we shall move to, so this is the actual definition of the Laplace transform. Okay. So here I'll explain the important points only. So existence of Laplace transform. This is very, very important for JNTU exams or any autonomous university exams. You may get 2 marks questions, very important question, 2 marks question. They may ask you, uh, what are the sufficient conditions? Yes, satisfied conditions, sufficient conditions. Okay. What is the sufficient conditions for the existence of Laplace transform? So you get questions like this. What is the sufficient conditions for the existence of Laplace transform? Very important question. There are 2 conditions. The first condition is f of t is piecewise continuous or sectionally continuous. I'll define it later. First, listen the points. The first point is f of t is piecewise continuous. The second point is the function f of t is of exponential order. Let us see the definition of these two. So first, remember these 2 conditions. So if any function is piecewise continuous, as well as if it is of exponential order, then only we can find f of t, the Laplace transform of f of t. So you may be thinking that one integral transform is enough, the Laplace transform is enough. What is the use of Fourier, Z transform? So hundreds of transforms are there. What is the use, you may ask? So not every function can have Laplace transform. Not every function can have Laplace transform. Only few functions can have Laplace transform. So some functions cannot have Laplace transform, can also be used for Fourier transform. So both, if Laplace transform, Fourier transform cannot, if we cannot find those transforms, we use Z transform. Like this, we see which transform is possible. So for that one, whenever a function is given to find evaluation of integrals or solving ODE, first of all, we shall check whether the function have Laplace transform or not. How do we check? Using this sufficient condition. That's why this is very important. Now, we shall check whether what is a piecewise continuous, sectionally continuous. You may be listened about the continuous function and discontinuous function. What about this piecewise continuous? Let us explain this using graphically. I'll explain here. Okay. So if you take a graph, a function, suppose y is equal to f of t or something, a function, or f of x we can take. So here in this case, x function, x-axis and y-axis. If we plot this curve, y is equal to f of x on a graph, so you must get a smooth curve. Okay, this is x-axis, this is y-axis. We might get a smooth curve. That is, if you may get like this, something like a continuous curve. There is no curves and everything. Suppose if a function has move to plus infinity and comes back, and it may move to minus infinity and comes back. Okay, there may be cut here. When go to minus infinity and comes back, there may be cuts. So if the curve is not continuous, so here the curve is continuous. So this function is called continuous function. If the curve is not continuous, so if we move to plus infinity or minus infinity, so then we say that the function is discontinuous function. The function is discontinuous. So leave about all these definitions, continuous and discontinuous function definition. Just I'm explaining graphically. So leave about the definitions. Okay. So there are some more functions may be there. They can be like this. Like this. And there are some functions like this. Suppose the curve is like this. So we say that this is discontinuous function. So we say that this is a discontinuous function. Okay. So because the curve is not continuous, so the function is increased up to here and comes back to negative part and comes to positive section. At the point x is equal to 0, the function is jumping from positive to negative. So it may jump like this. So this type of functions are also not continuous, discontinuous functions. Okay. And only the curve which is continuous, then so it's suppose if you take like this is a sine x function which is continuous, and if you take cos x function, so cos x function will be like this. It's also continuous function. So there is no curves and something. The curve is a smooth curve. Okay. So these are all cos. This is sine x and this is cos x. Okay. Okay. These are continuous curves. Okay. But if we move to plus infinity, suppose tan theta, tan x. Tan x is discontinuous at x is equals to pi by 2. Okay. It is discontinuous at x is equals to pi by 2. Tan pi by 2. Because tan pi by 2 value is infinity. So whenever it moves to infinity, we say that infinite discontinuous. But here it's not moving to infinite, but jumping from positive to negative, negative to positive like this. So because of that one, this is also discontinuous function. Here it is called infinite discontinuous. It is finite discontinuous. It is finite discontinuous. Only finite discontinuous can be called as piecewise continuous. The present topic now, if we come to the present topic is piecewise continuous. Here, what is a piecewise continuous? The main definition we have to learn. So I have explained what is a continuous and discontinuous functions. Okay, let us see about the piecewise continuous. Here, see, piecewise continuous are sectionally continuous. So only finite can have a piecewise continuous. Here, in this case, the complete interval AB can be divided into subparts A comma A1 and A1 to A2, A1 to A2, and so on, AN to B. So the complete interval. So from here to here, I divide the interval into parts. So one part. This is in this part, it is continuous. In this part, the curve is continuous. Here, if you observe this, from here to here, the curve is continuous. From this point again, from this point to this point, the curve is continuous. From this point to this point, the curve is continuous. From this point to this point. So the entire interval is subdivided into divided into sub intervals, and in each interval it is continuous. So it is called continuous curve. Continuous, it's not continuous actually. Piecewise continuous or sectionally continuous. This is sectionally continuous or piecewise continuous. If you take another what do you call graph, if you take like this, here I'll write. Okay. So if you take another one which is piecewise continuous. Okay. If you take another graph, so if the curve is like this, suppose for example, the curve is like, it is not piecewise continuous. It is not continuous as well as not piecewise continuous. So from here to here, it is continuous, but from here to here, it is not continuous. There is no curve here. So it is not piecewise continuous. It's not sectionally continuous. Okay. So the Laplace transforms can be found only for piecewise continuous functions, as well as it is of exponential order. Here itself, the definition is there, exponential order, second condition. Limit t tends to infinity e power minus at f of t is finite. Okay, here I'll write here. So what is exponential continuous? So sorry, exponential order. Limit t tends to infinity. Okay, limit t tends to infinity e power minus at f of t is finite, exists. If the limit exists, we say that it is piecewise continuous. Sorry, it is of exponential order a. Okay, whenever if the limit exists, if it is not finite, so if it is not infinite, if it is finite, so f of t is said to be what do you call exponential order of a, e power minus a. So then f of t is said to be exponential order. So these are the two conditions. Very important question. So you may get questions like this. What is the sufficient conditions for the existence of Laplace transform? So we have to write these two conditions. Okay. And let us move to the first property, the main property. These properties works for satisfied by derivatives, integrations, and linear properties. And the derivatives integrations also satisfied this linear property. And the Laplace transform as well as inverse Laplace transform also linear property works. Okay. So what is the linear property? Nothing but we have to take constants of. Okay. So if you take so the Laplace transform, suppose if you need to find Laplace transform of, second. Okay. So if you need to find Laplace transform of a into f of t plus b into g of t. Here f of t, g of t are functions, and a and b are constants. So we can take constants. A outside, we write L of, that is Laplace transform of f of t, and plus b into b outside, and individually find the Laplace transform of f of t as well as g of t. So this is same as we have seen in the integrals and derivatives. We can take the constants outside and we derivate. Here also we take constants outside and find the Laplace. That is called linear property. Okay. So proof is not required actually. So proof is also there here. And let us see the basic formulae which are used in the first part, that is inverse, that is Laplace transforms. The proofs are not important. We shall see only the formulae. Okay. So here are the functions. So total 9 formulae are there, very easy formulae. Okay. So whenever we need to find the Laplace transform of a constant, here k is constant. So L of k is nothing but k by s. So the formula for L of k is k by s. So proof is defined by the definition of the Laplace transform. From this one, if you substitute in the place of f of t, if you substitute e power, that is k constant. So integrate, we get this one. The proof is not required actually. It's the time waste actually if you learn that one. Okay. Laplace transform of k is k by s, and Laplace transform of e power at is 1 by s minus a. Here s is greater than a. Okay. And a here, so we see the power of e exponential, and here if e power L of e minus it, so these two first, second and third formula are similar. Okay. Here the a is positive, here a is negative. In the place of a, if you put to minus a, minus of minus plus a, so same we get 1 by s plus a. And the Laplace transform of sin 80 is a by s square plus a square. Cos 80 is s by s square plus a square. If you observe, whenever we get sin, we get the numerator a. Whenever we get cos, we get the numerator is s. So here a is here coefficient. See here sin 80, coefficient of t, sin 80. So whenever we get sin, we get the numerator is a. Whenever we get cos, the numerator is s. The denominator is same, s square plus s square, s square plus s square. The same way sin h80 and cos h80 we shall see. Sin h80, whenever we see sin, we see the numerator a, and whenever we see cos, we get a numerator s, whether it is trigonometric or hyperbolic. Sin means the numerator is a, cos is the numerator is s. But the denominators for trigonometric we get s square plus a square. For hyperbolic, the denominator is s square minus a square. We get this one. So these four are similar. Sin 80, cos 80, sin h80, cos 80. And we shall see L of t, just simply 1 by s square. So these two, the 8th and 9th formulae are similar, because here see, if you observe L of, so first I'll explain this one. L of t power n. Okay, L of t power n is, the power is important here. N factorial by s power n plus 1. N factorial by s power n plus 1. Suppose in the place of n, if you put 1, we get this formula. In the place of n, if you put 1, t power n, t power 1. Okay. Here substitute 1, what do we get? So t power 1, here I'll explain. Okay. So L of t power 1. If you have substitute the same formula, 1 factorial by s power 1 plus 1. So what do you get? 1 factorial is nothing but 1. S power and 1 plus 1 is 1 by s square. So we get the same formula 1 by s square. So these two are similar. Okay. Here in this case, actually, okay, if you observe L of t power n, the actual formula is gamma of n plus 1 by s power n plus 1. Gamma of n plus 1 by s power n plus 1. This is the actual formula. But if n can be integer or a fraction, okay, integer, that is minus 2 plus 2. So the negatives are not defined here. The gamma function is not defined for negative values. The only positives, positive integers. Okay, positive integers. If you have integers, we write z plus positive integers, and you have fractions. Okay, here fractions. So whenever we get fractions, we use the gamma function. So if it is an integer, we use gamma of n plus 1 is nothing but n factorial by s power n plus 1. So here, if n is integer, gamma of n plus 1 is nothing but n factorial. So if gamma is what do you call, it's a fraction. So we write in the form of n into gamma of n. Gamma of n plus 1. If it is a fraction, we use this one. N into gamma of n plus 1. So like this. So gamma of n minus 1. If it is a fraction, we use n into gamma of n. If it is an integer, we use n factorial. Like this, we get it. Okay. These are the formula, important formula. Let us move to the problems now. Okay. So let us see a first problem. Laplace transform of this one. Okay. So let us write here. Let us see basic problems here. So L of Laplace transform, the first problem, L of e power 3t minus 2 into e power minus 2t. Okay. Sine 2t plus sine 2t cos 3t plus cos 3t plus sine h3t sine h3t plus minus 2 cos h4t minus 2 cos h4t plus 9. So in a single problem, I'm explaining all the formulae. In a single problem, we use all the formulae. Here, we apply the property, linear property. So we take all the functions, the constants outside here. So e power L of e power minus 3t minus 2 outside, and L of e power minus 2t, and plus L of sine 2t, okay, plus next L of cos 3t plus L of sine h3t minus 2 into L of cos h4t, okay, plus L of 9. Here I have applied the linear property. Here I have applied linear property. So direct formula e power at. Here a is nothing but 3. Okay. So what's the formula e power at? 1 by s minus a. So we can see the formula here. E power at is 1 by s minus a. Here in this case, what is a value? 3. So we write 1 by s minus 3 minus 2 into e power minus 2t. So whenever we get minus, we get 1 by s plus 2. So here e power minus at is 1 by s plus a. 1 by s plus a. So we get like this. Okay. And next here plus sine 2t. Sine 2t is a by s square. Here in this case, what is a? 2. 2 by s square plus 4. So a by s square plus a square. A value is 2 by s square plus 2 square. What is 2 square? Nothing but 4. I'll write 4 directly, and plus 3 cos 3t. Here cos 3t. Cos 3t is s by s square plus a square. So you can see here cos 8t is s by s square plus a square. So here in this case, s by s square plus a square. What is a square? 3 square is nothing but I'll write 9. Okay. Plus cos h 3t. So whenever we get, sorry, sin h 3t. Whenever we get a sine, we get a by s square plus 9. Okay. A by s square plus a square. Here plus, not plus, minus. So whenever we get a hyperbolic, we get minus. Sin h 80 is a by s square minus a square. And here minus 2 into cos h40. That is s by, whenever we get cos, numerator is s square minus, since it is hyperbolic function, we get minus 40, 4 square, that is 16. Okay. Plus L of k, first formula, k by s, that is 9 by s. L of k, first formula, L of k is nothing but k by s. Here in this case, k value is 9. So this is the thing. So simplification, we get the actual problem, actual solution. Okay. And we shall see the next problem. So this is the solution. Simplification by we get this one. So it's not clear actually. I have written here. So this is the solution. Okay. Okay. Now let us see about the conditions, sufficient conditions. What's the sufficient conditions we see? So the sufficient conditions, first one is piecewise continuous. Okay. Piecewise continuous or sectionally continuous. Another one is exponential order. We shall see the problems related to piecewise continuous and exponential order. So let's second problem is on piecewise continuous problems. So whenever it is predefined functions like this, we apply directly the formula. Okay, you may ask you the question like this: where is the Laplace transform of sine tan 80? Sine cos is there. What about tan 80, cot 80? Because tan 80 and cot 80 are discontinuous functions. Not all functions have Laplace transforms. Okay, only few have Laplace transform. The limitation, based on the limitation, because of the limitations, we have another transform, remaining many transforms. Okay, so next here, the second question is like this. So the question is like this: find the Laplace transform of f of t defined by three values 0, 1, 2. 0, 1, 2. 0 if 0 less than t less than 1. If the t value is between 0 to 1, the value is 0. If the t value is between 1 to 2, the value is 2. And value is 2 if t is greater than 2. If t is greater than 2. So if I explain this, if I plot this on a graph, okay. So if t is equal to 0 to 1, here suppose instead of x, I'll take t, okay. And here I'll take y, okay. So the value of here the 1, and this is 2, and here y value is 1, here is 2. Suppose for example, t is 0 to 1. 0 to 1, y value is 0, okay. And if for 1 to 2, t value is 1 to 2, y value is 1 to y value is 1. So y value is parallel to 1 here. And here the 2 above, the value is 2. Y value is 2. So like this, if we take 0 to 1, 1 to 2, and 2 to infinity, the values are like this is piecewise continuous, not discontinuous. This curve is discontinuous curve. So, but piecewise continuous. Why piecewise? If we take 0 to 1, the complete 0 to infinity interval, okay, I'll divide into piecewise, that is 0 to 1, 1 to 2, and 2 to 3, like this, and so on. So 0 to 1, it is continuous, 1 to 2, it is continuous, 2 to 3, and 2 above, it's completely continuous. Okay. Okay. Now, okay, let us move to the actual problem. So whenever we get questions like this, we cannot use the formula directly. So we have to use the definition. What's the definition of Laplace transform? L of f of t is integral 0 to infinity is e power minus ht f of t dt. Okay, so here we divide the integral into three parts. 0 to infinity. So we divide into three parts, that is 0 to 1, 1 to 2, and 2 to infinity. So we divide it. So 0 to 1, e power minus ht f of t dt plus integral 1 to 2, e power minus ht f of t dt and plus integral 2 to infinity e power minus ht f of t dt. Here we substitute the values integral 0 to 1 e power minus ht into f of t. The value of f of t from 0 to 1 is 0. So we substitute 0 here and plus, so here dt. Okay, and plus integral 1 to 2 e power minus ht. F of t is defined 1 to 2 is 1. So we substitute the value of 1 here plus integral 2 to infinity. So 2 above here, 2 t greater than 2 means 2 to infinity e power minus ht, 2 greater than 2. So t greater than 2, the value is 2 dt. Here also dt. Okay. And here anyway the first value is 0 and second value 1, the constant. So e power minus ht integration is e power minus st by minus s from 0 to infinity plus e power minus ht. So here 2 I am taking outside, e power minus ht 2 outside by minus s. The integration is same but the limits are different. So 0 here it's not 0 to infinity, here it's what, 0 to 0 also wrong, 1 to 2. The limits are 1 to 2. The limits are 1 to 2. Here the limits are 2 to infinity. Okay. And here in this case, so I'm taking minus 1 by s outside here. E power minus st upper limit. Substitute upper limit as in the place of t, substitute 2. So we get e power minus 2s minus e power in the place of t, substitute lower limit 1, e power minus s. And next here minus 2 by s. Here I'm taking minus 2 by s outside. In the place of t, substitute upper limit. So we get e power minus infinity minus e power minus 2s. Okay. So here in this case, the values becomes what? So 1 minus 1 by s minus 1 by s. Okay. The value is what? E power minus 2s as it is. Okay. Here e power minus 2s. And next minus into minus plus 1 by s e power minus s plus 1 by s e power minus s. And next here e power minus infinity. This is nothing but minus infinity. E power minus infinity is 0. Next term is completely 0. E power minus infinity is 0 if you can observe the value. So the last term, fourth term is, so minus into minus plus 2 by s into e power minus 2s. Yes, that is 2 by s into e power minus 2s. So we can join these two terms, e power minus 2s terms. So 2 by s minus 1 by s. 2 by s minus 1 by s is nothing but 1 by s. 1 by s e power minus 2s plus 1 by s e power minus s. So we can take 1 by s common. Okay. So these are the solutions. So we can divide into three parts, 1 to 0 to 1, 1 to 2, and 2 to infinity, and substitute those things. And finding the solutions, we get 1 by s. We can take 1 by s common, e power minus 2s plus e power minus s, like this. Okay. So these are the thing. And we can move to similar problem. I'll move to the similar problem like this here. what do you call this is a piecewise continuous problems. Okay, find the Laplace transform of f of t. Okay, here the question is, I'm moving to third question. Find the Laplace transform of f of t. So f of t is defined by cos t for t is from 0 to 2 pi, 0 less than t less than 2 pi, and next is 0 if t is greater than 2 pi. Okay, so here also we use the definition. So that is, what's the definition of Laplace transform? L of f of t is uh, integral 0 to infinity e power minus ht f of t dt, f of t dt. So using this one, we convert this integral 0 to infinity into two parts, 0 to 2 pi and 2 pi to infinity. Anyway, 2 pi to infinity is 0. So we get 0 to 2 pi e power minus ht. Here directly I'm substituting f of t value. What is f of t here in this case? Cos t. Cos t dt. Next plus integral 2 pi to infinity e power minus ht into f of t. Here in this case, what is f of t? Is nothing but 0 to 2 pi to infinity. That is, the value is 0. The second term anyway we get a 0 value. Here we integrate only this one, and here we have a formula. I'll write here formula e power at cos bt formula. E power at derivative of, sorry, integral of e power at sin bt dt. Okay, cos bt dt. So the formula is e power at by a square plus b square into a cos at cos bt, okay, plus b sin bt. These are the formula. We use this formula here. Here in this case, e power minus ht, what is a value? Nothing but minus s. Here in this case, in the place of a, we substitute a is equal to minus s, and b value here in this case just 1. So b value is 1. Substitute those things. So what do you get? E power at. What is a? Minus ht. Okay, e power minus ht divided by minus s square plus b square, that is 1 square, into a cos bt. A is nothing but minus s. Here I'll write a is equals to minus s, b is equals to 1. Substitute here. So a cos bt, b is nothing but 1, plus b is nothing but 1 into sin bt. Sin bt. So this is the solution. So from the limits 0 to 2 pi. 0 to 2 pi. Let us substitute the limits in place of t. Okay, only t. And here in this case, e power minus st. In the place of t, we substitute 2 pi. Okay. So what do you get here? E power minus st. That is 2 pi s. By minus s square is s square plus 1. Okay. Into a cos, sorry, a is nothing but minus s. Minus s cos t. T is what? Nothing but 2 pi plus sin 2 pi. In the place of s t, and substituting first upper limit 2 pi. Now substitute 0 in the place of t. Substitute 0, upper limit minus, now the lower limit, e power 0 by s square plus 1, and minus s cos 0, minus s cos t. T is nothing but 0 plus sin 0. Okay, here we have to observe the things. Sin n pi is always 0 for any value of n integers, minus infinity to plus infinity. So sin 0 0, sin pi 0, sin 2 pi 0, sin 3 pi 0, like this. Whenever we get cos n pi, the value is minus 1 power n. Remember, if n is odd, negative; if n is even, positive. That is, cos pi is minus 1, cos 2 pi is plus 1, and cos 3 pi is minus 1. Like this, it goes on. So using this, we can write like here e power minus 2 pi s by s square plus 1, and minus s into cos 2 pi value is anyways 1, plus sin 2 pi value is sin n pi is always 0. N value for any value, for any n value, sin n pi is 0, minus e power 0 is equals to 1, s square plus 1, and minus s into cos 0 is 1, plus sin 0 anyway 0. Okay. So we write the terms minus s e power minus 2 pi s by s square plus 1. That is here minus into minus plus s by s square plus 1. So this is the final answer. We can take 1 by s square plus 1, s by s square plus 1 common. Okay. Here we may get a solution like this here. S by s square plus 1 common, and e power minus 2 pi s, 1 minus e power. So 1 minus e power minus 2 pi. That will be the solution. So in this part, we have seen about some basic problems. In the next part, we shall see the remaining basic problems. That is the problems related to the basic formulae. Okay.